Nice to be in orbit.
Thank you for coming. I'm Ron Reedy. This is more about Peregrine as an example of creating a company, of being entrepreneurial, of going through what does it mean to the many, many books about it, crossing the chasm, inside the tornado, etc. I was just telling Terry Albert that I actually did the math, and including all of the Navy's research dollars that went into the technology, that I'll also cover the technology and what it was, so you can see, gee, how would you, maybe you can even do the thought experiment. If I knew that worked, what would I do with it? But the total research dollars, interestingly, come to about 15 million, which is a lot of money. Those of you who get grants know that $15 million is a lot of money. To get from proven technology to the company at the point that it was essentially close to break even, we raised another $200 million, spent all of that. We had in-kind contributions from partners of close to between 50 and another 100 million. We spent all that. We had almost $500 million of revenues that came in, spent all that. If you add it up, it's more than $750 million of cash that went through this company to get to the story you're about to hear here. And so it's one of my favorite phrases from the movie The Right Stuff, Thomas Wolfe book. And my favorite phrase, that's a very big book, but my favorite phrase is, at one point, one of the hotshot jet jockeys is saying, you know, why do I have to give you an interview? You're just a reporter. And the reporter looks at him and he says, no bucks, no Buck Rogers. And that's the story here. $750 million. And if I'd have thought it was going to take that much money to get here, I would never have even considered starting it. So it's, you know, it's lucky not to know. I wish I didn't know now what I didn't know then, to quote the famous rock song. So this is what I'm going to do. I'm going to give you some personal perspectives. That gives you an orientation of just how I think. Then I do want to go into a little bit of the semiconductor business. Peregrine and our technology, I'll cover this. We do RF, we do wireless things, that's it. Everything you'll see has to do with that, and I'll get into some detail as to what the advantages were. This is an IEEE, and as I remember, one of those E's stands for electrical engineering, or two of them, so we'll cover that. Then I want to do a little bit of this history. I decided to start the company 25 years ago, and I'll go through some of that thought process as well. These are my personal perspectives. Personally, I've always rooted for the underdog. I'd much rather root for the Cubs or the Padres than the Yankees. Rooting for the guy that wins 1/3 of the time, I just want to root for the guy when finally the upset happens. I want to be on that side of the fence. The Coyote is way more interesting than the Roadrunner. The Roadrunner can run fast. The Coyote's always got these cockeyed schemes of, you know, Acme anvils that he's going to drop off of the top of the rock, and something always goes wrong and he gets splattered against the painted on. But he gets up and he dusts himself off, and he somehow he knows the next time, by golly, he's going to catch that Roadrunner who can say beep beep and run fast. And third, my observation in nature is most members of a herd either get trampled or eaten. So that's not really the place you want to be. You're much better off kind of off by yourself. In other words, I'm a dedicated card-carrying contrarian, and that gets me in trouble, but it's just how I think. In 1988 actually, but I started writing business plans and actually putting effort into this. In 1989, I decided to start the company. I really thought $5 million would do it. By 1995, I thought we'll either be out of money or we'll be dead. We'll be one of those footnotes on history. And I already mentioned, since then, we raised $200 million. We went through 9 different fabs. We're in the semiconductor business. That means you need a semiconductor fab. We went through 9 of them. We actually bought one, not me. I wasn't CEO at the time. I was replaced as CEO when the new guy came in. I said, you've got to make a decision that I couldn't make. If you just do what I was going to do, what's the point of changing? We need something. Something's wrong here. He decided this moving from fab to fab was killing us. So we had to buy a fab. I thought he was crazy. He was right. He saved the company. And I can't count the number of near-death experiences, the number of times officers had to write paychecks. We told the employees we're almost out of money. You keep improving the company, we'll go get the money. And you know what? In all of those near-death experiences, we never lost an employee. I never saw somebody with resume writer worried about their job. They trusted us, we trusted them, and it worked. So, with all of that, if you're still interested in listening to this, this talk, I've discovered there's kind of 3 general rules that you can live by in terms of business. The first rule is capital comes with instructions. If somebody writes you a check, they are giving you instructions. You're buying something, they're giving you something. When you write that check, when you pay for a hamburger, you're telling McDonald's, I like the Big Mac or I don't like the fish fries or whatever it is. So capital is big piles of money, and it's incredible how many people who have the capital will tell you by writing a check or not writing a check. So you have to read those instructions. You have to listen and trust the capitalist system. Because if you look around yourself, everything in this room and everything in your life is in your life because an entrepreneur at some time decided to take an idea and go start a company and sell a product. So the US is the integral over all the great entrepreneurs, and some of those failed and some of those succeeded, but they all followed this general rule. Rule number 2, I have not seen this violated very often. Almost everything takes pi times longer than you think, and that means it costs pi times as much. And it's kind of amazing how close to 3 it is. It just works out that way. I kind of track this. I have friends who are going to refurbish their kitchen. Oh yeah, we're going to have it done by Christmas. Yeah, guess what? Next year. 3 months and they daily out the wall, and what do they find? There's no pipes in there. There's a rat's nest. There's mold. So that's just get your best estimate, and then if you really want to know what's going to happen, keep track of rule number 2. And rule number 3 is kind of the most interesting one. In my opinion, information has no value except when it's in motion. So if any one of you in this room actually does have the cure for cancer, you don't write it down, you don't tell anybody, you don't start a company, you don't ask for FDA approval, you never tell anybody, and then you die. Did that information ever have any value? And my answer is no. A corollary to this is, if information has value when it's in motion, it has more value when it's in motion faster. Now, information can have negative value. A rumor that the president was shot can cause the stock market, could do any number of things. There are people who intentionally put out lies in order to try to cause a negative reaction somewhere. So the value can be positive or negative, but the value comes from motion, and its value amount is proportional to its velocity. An example of this is there's a dictatorship that ruled a country in Africa for over 3,000 years. That dictatorship was unassailable. The dictators were called Pharaoh and King and General. This is Egypt. And Egypt was knocked over by Twitter in 3 months. Now they're back and the story's not done, but the fact is a dictatorship of 3,000 years could not stand all of that information in motion. We're going to move where the demonstration is 2 blocks over. So the army's over here and the demonstrators were over there, and by the time they moved, they moved. So it's an absolute classic example where putting information in motion had an enormous impact. Semiconductors. It's about a $300 billion a year industry. That's about 2/3 the size of Walmart. Who cares? I mean, really, Walmart is $450 billion. So who cares about semiconductors? Why do we care? Why does it get so much? There are way more analysts on all the semiconductor companies than there are on Walmart. So what does it matter? And the reason is it has this immense multiplier effect that a system or the total system value, take a cell phone. The cell phone might be 20 or 30% semiconductor content. There's a lot of software, there's batteries, there's all sorts of stuff in there. And then that gets sold and you pay $50 a month because of those semiconductors, and then the cell phone company and all the people that open table to get reservations, the spin-off value of the semiconductors in the cell phone are anywhere from 10 to 100 times the semiconductor content. That takes that $200, $300 billion a year industry and turns it into a trillion up to $10 trillion industry. What good is the Joint Strike Fighter without electronics in it? You wouldn't build it. Automobiles now have way more electronics in them than they do steel, rubber, everything else combined. It's a rolling electronic platform. So it's the leverage value of semiconductors, which means you have to look at all these factors when you're thinking about semiconductors. And so inherently, anything, getting back to that information has value when it's in motion. What puts it in motion? Semiconductors. So that's where it derives its value, even if the inherent value of the pure chip is not as big as you think. Closest industry I can find for the semiconductor industry is the oil industry. It's mature. The oil industry has been through about 5 or 10 generations of life. The semiconductors industry has actually been through about 20. Their generations are shorter, but fracking with directional drilling and thermal and sonar mapping, that's maybe the 5th or 10th great idea of the oil industry. We change every 18 months. We completely rewrite the rules every 18 months or 3 years with a new fab. The big elephant fields, the 5, 10, 20 billion barrel fields, they're all discovered. They're called microprocessors. They're called Qualcomm. They're called DRAMs. They're there. But the wildcatters are actually interesting. What is shaking up world energy markets more than anything else? Fracking. It's completely changed the world dynamics. It's knocking Russia out of its dominance of European gas. It's changing everything, and the man who basically put fracking in business just died, and he got his obituary into the Economist magazine, which tells you he was a big name in the world. So it's the new ideas, it's the wildcatters, and they're called wildcatters in the oil business. They're called startups in the electronics business. So if you want to know what's going to happen, watching the big guys, the Exxons, who are figuring out how to plug a 1-ounce drip in every mile of pipe, which turns out to be 10,000 barrels a day. It's a big number. I'm glad they're fixing the pipes. It's not going to change the world. Fracking is going to change the world. And usually what looks like a niche opportunity ends up being a big deal. And that's the beauty of startups. Big companies can't afford to go into niche opportunities. If you're already doing 10 billion a year and you see a new opportunity for 10 million, who cares? Our costs of goods, if our prices are going down 1%, we're doing 10 billion a year, we're going to lose 10 or $100 million a year just in cost erosion, price erosion. I can't, 10 billion, I'm going to invest 2 years of R&D for a new thing for 10 million, doesn't move the needle. The needle's too fat. So that's why startups inevitably are the mammals and the big guys are the dinosaurs. Exxon didn't bring us fracking. Chevron didn't bring us fracking. Some unknown oil company up in North Dakota brought us fracking, and it's literally changing the world, may make the US energy independent again. Who'd ever thought that in our lifetime, forever, we'd ever see that again? So Peregrine, who are we? I'm going to give you this. This is the answer, by the way. This is where we got to. Then I'll get into how did we get here, and what did it take to do it, and what were all the mistakes we made. We do RF components. We have been growing on average around, Dan, 30% a year for the last probably 8 or 10 years. And I'm going to go through that not in dollars but more in unit volumes, because semiconductor volume drives the semiconductor industry. We have basically mobile phones is about 75% of our revenue, meaning cell phones. We're in every smartphone manufacturer. We're in all of them. We're every Apple, Samsung, you name it, we're in it. And we also have a very large business in, I just call it industrial. So it's everything from medical to automotive to test and measurement, public safety radio, cable TV, television sets. If you own anything 34-inch and above HD TV, you have at least one of our chips in there. So we have an enormous number of customers here. And then we have what we call high performance markets, which I've mentioned some of, one of which is the space market, which has an incredible, it has a sex appeal to it. It's Star Trek. It's just really cool. And I'll tell you a story that embodies it to me about the coolness of where our chips have actually gone throughout the solar system. These are some of our bigger markets. These are our customers. What you'll notice here is we have the tier 1 customers not only in all of these markets but in all of the cell phone markets. And there's a reason for that. One thing Peregrine could absolutely articulate from day one was we were different. We were going to do silicon CMOS, ho-hum, I've heard it, on Sapphire. And a technology rejected by every major semiconductor company in the world over 30 years. RCA, Intel, HP, Motorola, ST, IBM, you name it, they all had a silicon on Sapphire program. The reason? The performance. It's just brilliant. You get rid of capacitance and the world gets better. They didn't even think of RF. Turns out that's what we used it for. But we actually decided we would do this completely different thing. And the tier 1 companies are tier 1 because they lead. And they stay in the lead by looking for new things that keep them in the lead. The followers, and anybody who wants to be an entrepreneur, if the people you're meeting in that opening meeting say, to your question, what do you really need? If they say, I need what I'm getting today, only cheaper, close your book, thank them profusely, and get out of the room. You're wasting your time. You do not put $250 or $750 million into a company to help a buyer lower his cost of goods. That's just lunacy. You do it because you convince the company that your capability is going to improve their capability, and they're going to win in the market because you're doing something different, and they're enough of a leader to take that risk with you. So these are all of the top companies in these markets, including in our handset market, and that's why. They liked the fact that we could clearly articulate how different we were. This is ultimately the measure of success in any semiconductor industry company. We here just last quarter shipped our 2 billionth chip. We ship those chips today at about a 0.1 part per million field failure rate. In other words, we ship 10 million chips and we get 1 back. And about half of those that come back were misused by the customer. We just say we can't confirm the error. We don't tell them that they dropped it or they ESD'd it or whatever they actually did to it. We get them back with holes drilled in them and they say, we don't know why this chip isn't working. Really? Did you look at it? You might want to find the guy with the rogue drill. So that's 2 billion units. This is one of the most out-of-body experiences for me to say that. To ship 2 billion of something to it with the complexity of what we do, to the standards that a farmer can't live up to. I guarantee you there's no farmer in the world that can ship 10 million soybeans and guarantee only one of them has a mark on it. Or 10 million ears of corn that doesn't have one of the kernels missing. Because to our standards, that isn't a good ear of corn. So the standards to which the semiconductor industry is held is just by far the greatest in the world. Man makes semiconductors better than anything else on the planet. Bill Gates or Microsoft launches a brand new software system and they admit there's 50,000 bugs in it. Right? And you know they're lying. You know there's 250,000 in there. They just don't know about 200 of them.
I thought it was only a factor of pi.
Yeah, you're right. Thank you. It's 157.2. I should have. I'm going to use that. Thank you. I'll quote it.
Free of charge.
Huh. But what you notice here, this is on a linear scale. I'm going to show you it later on a different scale. But what you see on this chart is actually, in my opinion, the only valid measure of a successful entrepreneur, and that is exponential growth. Why? Because you grow in proportion to how much you have today. That says your customers like what you're doing and they put you in more products. Their competitors see what they're doing and they have to have your products. If you're stable and steady, you're either a mature industry, meaning you're well out of the entrepreneurial phase, or you're a cottage industry. I make the most beautiful quilts in the world and I have enough time to do 2 of them a year. That is fine, but it isn't an entrepreneurial experience. It isn't capable of undertaking exponential growth until you say, you know what, I'm going to go make these in China, sell them on the internet, turn it into a company, and buy the big boat or whatever. Our technology, in 40 years this year of working in semiconductors, it's very, very difficult to compare one technology to another. How do you compare one type of semiconductor to another? They're good for different things. How do you compare a Ford to a Mercedes? Well, people buy both, so it's just very difficult. But after 40 years, I've actually been able to reduce to a single chart that can compare any technology to any other technology. It's complicated. I'll spend some time on it. So I want you to pay attention. This is what I call the universal technology slide. And this is it. You've heard it from everybody, hence the universal. So the entrepreneur, if you don't believe this, you're not ready. You might be an entrepreneur, but you don't have the right topic yet. Because there's actually two important pieces of information here. One, you have to be absolutely convinced that yours is better than theirs. You have to believe that. Even under bad news, even when you run out of money, even when you get kicked out of a fab, you still have to believe you are better than they are. Almost as important is you also have to believe that they are worse than you are. Right? So there's two axes, there's two pieces of information here. So you have to be able to explain this to your future partners, your future manufacturing, your supply chain, your customers, all those people who give you that information through the capital system, whether they're investors or buyers or partners or co-developers. You better be able to explain the universal technology chart to them, and make sure you scrub this before you give up your day job. Hi, I'm Ron. I'm a CMOS-aholic. I pushed my first CMOS wafer in 1973. In 1973, there was one and only one user of CMOS. It was called the US military. The US military actually saw it as a technology in reserve against the Cold War, the evil Russians. They had 50,000 main battle tanks, actually true. We had 5. But what we had was 50,000 smart battle tank eating missiles, and they didn't. So as long as our missiles were smarter than their tanks, we had the famous mutually assured destruction, and missiles are way cheaper than tanks. So it was a technology war, from the Trident missile to CDMA that was developed at Linkabit for surreptitious communication. It was a technology war. And CMOS, when I used to work for the Navy, I have some of my old Navy colleagues here, we actually felt it's great news that CMOS is absolutely hated by the industry. Andy Grove was quoted as late as 1980, "We'll never use CMOS, ever. I'm going to replace a nice fast NMOS with a stupid slow PMOS that's twice as big. Oh, and it latches up? Really? Twice as many processing steps? I already can't yield this stuff." By 1983, he was on his knees in front of IBM begging for CMOS, and had to give 30% of his company to IBM to get CMOS technology. But before that, it was this slow, dumb, expensive, latch-up, ridiculous, interesting lab experiment called CMOS. But the military loved it. Why? Remember those tank-eating missiles? They needed pattern recognition. They needed sophisticated guidance. They needed eventually a GPS receiver. And I attended a meeting once at the Navy lab. Terry, maybe you were there. And it was, I believe, right after the Falkland War. And there was an admiral. He had one of those arrays of awards that actually went up over his shoulder. It actually looked like a kitchen towel. It was so big. And the guy gets up and he says, "Gentlemen, you have done an incredible job." The Navy lab was one of the absolute early pioneers in digital signal processing, mostly for sonar. They could pull the sound of a cavitating propeller from the SOSUS system from 100 miles away and screen out all the whales and the clicking shrimp and all that stuff. These guys, the technology was incredible. This guy gets up and he says, "Gentlemen, ladies, you have created the capability for us to accurately put a dent in any ship in the ocean. We can hit it, and we can hit the one we want. But the electronics consume so much power, it runs so hot, that we have such a big cooling system in there that there's no room left for a warhead. So we can bink it, but we can't boom it." And I thought, you guys need CMOS, because they were using emitter-coupled logic, which is a good way for a space heater. The computer's this big, the cooling tower's out back. Ask Cray. So CMOS was this idiotic, expensive, complicated, latching up technology that, oh, by the way, didn't consume any power, at least except when it switched. But by any other standard, it essentially was looked at as almost a non-thermodynamic machine, which is how can it possibly do any work and not consume any energy? It turns out it can't. But it was orders and orders of magnitude better than anything else anybody had ever come up with. The military grabbed onto it. Everybody else rejected it for cost reasons. And that goes back to that earlier comment. If you're going to think about starting a company, cost isn't on the list. Performance is. Value is. What are you going to do? Everything was too expensive, including what is now the almighty CMOS. 99.69% of all transistors ever made were CMOS. It used to be rejected, too expensive, useless. CDMA, early on, go read the newsprint. It's too expensive. It'll never work. It's too linear. It's hang a transmitter in your tree and bring down your system technology. But it got there, not because it was cheap, but because it used a more valuable resource than money, which was radio spectrum. The value is there. Forget about cost. You have to, if you want to drive down cost, there's only one thing that drives down cost: volume. Whatever it is, lithium batteries, guess who developed it? The Navy lab down the street. Why? Because they needed that space for warhead in those torpedoes. That's where lithium batteries came from, is torpedoes. They were so friggin' expensive at that time. If you just said, hey, do you think you might use one in a $200, $100 consumer device? No way. Everything's lithium-ion batteries now. Why? Volume. Volume gets you on that exponential growth curve, which says I can make more money if I can get my costs down. The volume absorbs all my overhead costs and my manufacturing costs. It's worth it for me to actually get a more efficient process because of the volume. If I'm not going to have the volume go up, why would I spend some money to make something cheaper? I'm not going to make any more money. This was the technology when I started. I have done everything from indium phosphide to cadmium sulfide to lithium tantalate. I'm kind of a materials device junkie. When I saw the first CMOS idea, I literally looked through the microscope, saw what it looked like, and thought, this is going to take over the world. There's no way anybody can compete with this because it is so low in power, and therefore you can scale it and scale it and scale it, and that turned out to be exactly what was needed for Moore's Law to stay alive. If we didn't have CMOS, Moore's Law would have ended in the 1990s because of cooling problems. The 386 computers were catching fire. You couldn't cool them. There was no way to cool them. They just burned literally their sockets. So without CMOS, the technology really would have died. Here's bulk CMOS. Here's what we do, which is this is not to scale vertically. We actually, when I was at the Navy lab, I was fortunate enough to be the branch head of the Navy's R&D microelectronics group. And I always say that what happened was when IDT left HP, they were the first startup company based on CMOS. There was literally an emergency meeting at our lab, and all of the brain trust of the Navy said, what are we going to do? Because if CMOS goes public, in 10 years the Russians have it. They'll still have 50,000 tanks. They can smarten them up. And then the balance of terror is actually really at risk here. So that brain trust put on a little pachinko ball the question, what's after CMOS? And they dropped it into the DoD pachinko machine, which is 485,000 little buttons, and it bounced around, I don't know for how long. And literally one day it came out of the little chute over my desk. It landed on my desk. And the question was, what will we, the DoD, do in 10 years if CMOS goes public? And I thought, that's a really good question. Wonder why they asked me. I was 25 years old at the time. I didn't have a clue. So I thought, well, maybe I'll go look into why did technologies change in the past? After all, NMOS wasn't the first technology, nor was PMOS, nor was I squared L, nor was ECL. The first technology that received the Nobel Prize was RTL, a transistor with a resistor. It was basically an analog gain block used as a flip-flop, and that got the Nobel Prize because the resistor and the transistor were integrated. It did lead to the integrated circuit, but that technology quickly ran out of the ability to scale because it consumed too much power. So I went back and I plotted, forget how many transistors are on a chip every year. Wonder what it looks like if you plot the power consumption of the best chips by year. And instead of being the straight line that was Moore's Law, It turns out it's a sawtooth. It goes up, you use the technology until it hits right around 5 watts per chip, because that's about all you can air cool. After that, you got to start doing something else. You have to do mounted fans, you have to have blowing, you have to do water cooling, you have to do something to cool these things, or the chips just fail. So you go RTL, then you replace the resistor with a diode, DTL, then you replace the diode with the transistor, TTL. You run it from typically a 10x reduction in power. You run it up until you put 10 times as many chips. It consumes too much power, and you replace the diode with the transistor, and then you discover Schottky clamping. Anybody remember TTL LS? The S stood for Schottky. It was brilliant. It was another one. Then there was I squared L and ECL and PMOS and NMOS and VMOS and DMOS and ABCMOS. And in that bag of tricks was CMOS. So I thought, that's interesting. Power is why people change, because they can't continue to use. Nobody retools a whole industry because they want to. They only retool an entire industry because they have to. And they had to when the chips were failing, which means they were overheating. So I thought, well, let's see, CMOS, wow, this instead of a 10x was a 100x improvement. But if I take Moore's law and apply it to that button and draw it out, it turns out in 1989, CMOS will hit the power consumption crisis of every other technology before it. Remember, at this time, CMOS is this idiotically low power-free system. Nobody believes CMOS would ever hit a power consumption because it was so much better. And in 1989, the 386s started burning up. And they had to go from 5 volts to what? 3.3 volts. In other words, gee, take those numbers and square it. Guess what? That's, again, one of those sawtooth things. So then we went to 3.3 volts and 2.5 volts. And we're down to what? 0.7 volts and all these incredible advancements in CMOS. But every one of those is a new tooling, new design tools, et cetera. So when I looked at this guy's problem, I said, we got to do something that's lower power. It's not about speed, it's about power. And so the only way to really dramatically reduce the power consumption was to get rid of the capacitive, the capacitors under these junctions, which on a real drawing would be huge. And charging and discharging those capacitors is what causes the CV squared F problem. And that's why everybody tried to do SOS for exactly that reason. You get rid of the capacitors, it goes faster. You get rid of the capacitors, it uses less power. It sounds like snake oil. I promise if you just take a drink of this, not only will your rheumatism go away, I mean, it was like, how can something go faster and consume less power? That's why all those companies tried to do this. The physics is compelling. The yield was awful. It was so expensive, it wasn't useful. If you look at other processes that are used, especially in RF, you have silicon germanium, which is a bipolar, integrated with CMOS, so you have silicon germanium by CMOS, but it still has the CMOS problems. And this is a bipolar. So it's good for certain things, but it isn't good for switching. And again, 99.99999% of all transistors ever made, they switch. They don't amplify, they switch. That's what a digital computer does. It goes from 0 to 1 and 0 to 1. It doesn't care about the in-between state. In fact, it wants to get between 0 and 1 without ever seeing an in-between state. It would love to be a vertical line, but it just can't do that. So if you really look at the world of electronics, it's made up almost entirely of switching things and a few amplifiers so that we can hear the results or transmit some power. And in order to do that, this is one of the truly great inventions, was the gas HPT, invented up the road by TRW. Thanks to the Department of Defense funding. It's a magnificent amplifier. It makes great power amplifiers. Bipolars just don't make switches, so it's very good for certain things, and each of these technologies has their space. But this is the one that I believed would replace CMOS for that military function, and I believed if we could fix the yield problems on this and do that in a way it would go into a commercial fab, then we could solve the DoD's problem. And so my job, and I got the funding for 10 years, was to find a way to make this commercially viable in a commercial fab at commercial yields so the military could use it. So we did that. What we ended up with is what we call ultra CMOS, which is sometimes 1,000 angstroms, sometimes only 600 angstrom thick layer of near virtually perfect silicon, sitting on the world's best RF substrate, Sapphire. And when I started the company, I thought, don't get in the way of CMOS. We'll never break in. We can't keep up with digital. So we have to do something that's different. We have to rely on the silicon is there, and it's just going to be CMOS. We have to differentiate ourselves on the substrate. And the two properties of Sapphire that I really liked were it is literally immune to all RF signals. It doesn't create distortion. It can't conduct current. It was a perfect RF substrate. It was also optically transparent. So we looked at, should we be kind of in the display business or the RF business? RF sounded like integrated circuits. Displays didn't. So basically, it was almost arbitrary. I just believed there was a bigger market in RF. So that was what we decided to do with the technology that we developed at the Navy lab over about 10 years. Here's how we did it. This is the work getting from here to here is what we actually developed at the Navy lab. If you grow silicon on Sapphire, it turns out it's not a crystal match. All of those defects had all sorts of side effects which were really problematic. If these defects got up to a gate oxide or if they caused problems with a threshold over the sizes of the chips, you just ended up with a 5% yield. I mean, look at this stuff. Imagine trying to make a Pentium in anything that looks like that. It's just unimaginable. So we set out to fix this, and we used an invention made by HP, worked with the HP inventors. They had decided to get out of this business, so we picked up the work. And basically through a process called SPE, solid phase epitaxial regrowth, what we did was we learned the recipes that said if you implant silicon in here and destroy all the crystallinity. The good news is you got rid of all the defects. The bad news is you got rid of all the crystal. So what do we do now? Well, it turns out if you heat it up, and the only reason we're here today is nature threw us a bone. It turns out what we want is 100 silicon. And the growth rate of the pieces of 100 silicon in between all these defects is 10 times higher than the growth rate of the defects. So all you had to do was heat it up. And the fast good stuff grew faster than the slow bad stuff. So we ended up with a nice lawn of thick grass, and all the crabweed was down, and we never even saw it again. Then we did a second implant deep enough to get rid of the defects on the bottom. Same process to have it grow down till it hit the Sapphire and it stopped. We turned on steam, which turned silicon into silicon dioxide, strip it off with hydrofluoric acid, and voila, you have bulk silicon grade silicon on a perfect RF substrate at any thinness you want, because the thickness was controlled by the oxidation step, not by deposition accuracy. And oxidation is the most controlled, thermal processes are the most controlled processes in the silicon system. So we got from here to here. We now have this material. It's very, very thin, which means we can scale the transistors, because transistors have to be at least 1/5 as thick as they are long, wide, whatever you want to call it. And so if you want to make a shorter transistor, you got to have a thinner silicon. This stuff didn't work because the thinner you got, you can see the defects are even worse down here than they are up here. So the thinner you got, the worse it got. This stuff fixed all of that, and that was when basically Graham Garcia, Mark Bergner, and I published a paper and essentially said we think we fixed silicon on Sapphire. That's in our history monograph out there. That's what we're calling the aha moment. That's when I realized the technology was fixed. We did what all those companies hadn't done with 6 researchers in a buried government lab, literally underground. And we actually had done something the industry hadn't done. And I started thinking, maybe this technology deserves one more chance to win in the commercial market, which is exactly why I decided to start the company. So what's the advantage for RF? Well, this is what a bulk silicon transistor looks like in cross-section. And everything everybody likes to talk about is the channel between the source and the drain. This turns on if you put a nice high voltage on the gate. You invert the device and you create a conduction channel. You have an N+ source, you have an N+ channel, you have an N+ drain. Guess what? Put voltage on it, it'll conduct like crazy. That is the magnificent MOSFET, whether it's P channel or N channel. The problem is that to keep these devices isolated from each other, basically most people use what's called junction isolation. So if you put plus, say, 3 volts on the drain, there's a depletion region formed in the P region. The 3 volts all ends up terminating down here, so the substrate never sees that voltage, which means the neighbor doesn't see it. So if Bob Noyce had survived, he would have gotten the Nobel Prize but he died. You can't get a Nobel Prize when you're dead, only living people. So everybody knows he was the half inventor of the integrated circuits. He just didn't last long enough to get the prize. But these capacitors, one of the big problems, and I'll get into what happens here, capacitance of a diode goes as 1 over the square root of the voltage. In other words, it's a nonlinear capacitor. People try to use them for varactors, and you use them in ranges where the nonlinearity gets dealt with, and you dope things, but the fact is it's nonlinear. It's not a linear capacitor. And that turns out to be critical to why Peregrine has succeeded, because if you go from this device, and there's 3 of them, one under the gate between the channel and the bulk, one between the source and the bulk, and one between the drain and the bulk. The conduction channel has this term in it, which I'll get into, as well as the capacitors. If you look at what we have, all of those nonlinear capacitors are 0. If they were there, they'd be nonlinear. It's just that they don't have the other side of the capacitor. They're gone. The other term that really causes problems in linearity, and those of you, many of you are in the RF and wireless markets, linearity is absolutely the magic elixir of modern communication systems. It's why Broadcom is here. It's why Qualcomm is here. It leverages spectrum. If you have a linear system, you can get more data down the same path as you can, as long as you don't disobey Shannon's law. That's what Shannon's law actually says. But you need linear systems to exploit that, and that's why we have 8-bit QAM and then 32 and 64, et cetera, is we're trying to get more data into the same spectrum. And that comes from linearity. Linearity is king. So what we need is a really, really linear transistor, and guess what? The inherent current in a MOSFET has 3 basic terms. A times the linear voltage, B times the square of the voltage, and then this funny term that's the third 1.5 root of it. Well, it turns out if you take the third derivative of this term, guess what? That term and that term go to 0. Third derivative of v squared is 0. This term you never get rid of. You can keep taking the third derivative, the 10th derivative. It'll never go away. But if you don't put any doping in the channel, which is what N sub A is, in other words, you have what is called a fully depleted transistor, which is what we focused on from day 1. If there's no doping in the channel, N sub A is 0. So the capacitors are 0, the N sub A term is 0, the V and the V squared term are 0 to the third order. And therefore, when we launched the company, we had people like Steve Moss, who many of you probably know, Mr. Mixer worldwide. He stood up at European Microwave. His annual State of the World for Mixers speech, he got up and he said, every year I come here and tell you how to get a half a dB better mixer. I have 2 words for you, Peregrine Semiconductor. They've moved the mixer bar a decade or more because their transistors, as far as I can tell, I cannot find the linearity limit of these transistors. I'm measuring the linearity of the spectrum analyzers and the test equipment. In fact, it wasn't long after that we sold 1 million mixers and they all ended up in test equipment because Agilent and Rohde & Schwarz and everybody else found out the same thing. By definition, test and measurement people have to use the best components, or you're only measuring the test and measurement equipment. So with that, now I got to be honest, I didn't know what linear was. I'm transistor weenie. I had no idea. And we hired a bunch of RF guys, and one guy came in and he said, well, I'll work for you. I think the company's, but before I sign the document, I want to go in and measure the linearity of your mixers, of your transistors again, to make sure that I measured it correctly the first time. Because if your transistors are that linear, I don't know what we're going to sell, but we're going to make a lot of money. And I waited until he signed because I didn't want to scare him away. And after he had signed the offer letter, I said, Rob, what's linearity? And he started looking for the paper. But it turns out, and this gets back to that, don't be afraid, do something, believe something may come along. We had a great technology, I knew it, and I didn't know why. But that wasn't a reason not to get going. We would have never discovered that if we hadn't gotten started and started interacting and looking for what products to make and how to make them and who's going to buy them and what's the benefit, et cetera. For those of you who are circuit model guys, basically this is all the substrate stuff in a bulk silicon transistor, and that's all 0 for us. So that's where all that linearity comes from. And basically, this right here is the problem with MOSFETs. G sub M sucks. The best transistor nature ever gave us is the bipolar. It's beautiful. It has great gain. It has absolute threshold match, VBE. It's wonderful. It can handle power. It's just a magnificent transistor for everything except switching, because it saturates. You can turn them on fast, you can't turn them off fast. And so while G sub M is terrible compared to a bipolar, we had this switching transistor called CMOS, and now it was linear, and we knew we could do something with that. And that's basically, and the good news on a MOSFET is G sub M, it goes as 1 over gate length. So if you scale, G sub M gets better. Scale more, G sub M gets better. Well, to scale, you got to have thinner silicon. Oh, that's right, the silicon's perfect. So we had this, what our CEO now, Jim Cable, calls Moore's Law for RF. We can do everything in RF, and if we don't have good enough gain for an LNA, scale it. Go get a shorter gate length. The world's full of fabs that are way shorter than what we're using today. So this is what we do. We compete mostly with gallium arsenide. And this is where my title, and change in industry. When we started the company, everything in RF was gallium arsenide. We started selling mixers against gallium arsenide. We started selling switches against gallium arsenide. We then got into the handset business, and every gallium arsenide company was desperate to prove we were wrong. Why? Because gas fabs largely fill themselves up on switches. Switches are big area things. PAs are not. PAs are mostly 1 HBT, and then you do an incredible spaghetti of components around the queen bee, and you make a great PA. But you don't put much on there. You just make transistors. So to keep a fab full, and fabs don't run well half full. They don't run well third full. They are incredibly expensive. They're all fixed cost. You have to keep them full or you can't stay competitive. Most gas fab companies filled up their fabs on switches. So a CMOS switch was a serious existential threat. We had CEOs from Skyworks, from RFMD going into our customers. We saw them coming out, and the customer was telling us, you know, those guys are in here, they just dropped their price by 50%. They said your stuff will never work. They said it's never going to be reliable. Don't rely on a startup company. And my response was, if they're that sure of how bad we are, why did they just drop their price by 50%? And those companies stuck with us. Today, those companies now say we're the biggest RF-SOI switching companies in the world. Why? Because they stole all of our intellectual property and they copied it. Okay, that's for the courts to settle. But the point is, the gas guys are moving to CMOS, and they're closing their fabs. RFMD just sold the huge Filtronics gas fab that they bought 5 years ago. They just closed it. Most of the gas guys, if they're not in optoelectronics, which prints money for them, the fabs are closing, which means all the other stuff. We're squeezing them out from the bottom, and gallium nitride is squeezing them out from the top. You want a power amp? Really? If you really want a power amp, you're going to use gallium arsenide? Most of our customers are saying, not for us. We're going to gallium nitride on the power side, maybe the LNA. If we have a 50 watt switch, we'll use gallium nitride. So it's going to be a gallium nitride and RF-SOI world. We invented RF-SOI. We put it in production. We didn't invent it. Guy up the road at Rockwell actually invented silicon on Sapphire in 1963. But we perfected it. We invented it in the commercial sense. And we put it in the market, and we spent $750 million doing it. And that is basically the story of the entrepreneurial experience here. This is technologically a work of art. It's unbelievable how hard it is to make an HBT and how good they are. But they're simply not going to compete with CMOS PAs. Why? Because CMOS PAs can be integrated with CMOS switches and CMOS tuning elements and CMOS other things in the RF front end, and all the power supplies and all the digital logic. It's all going on a single chip. And I challenge you to find any time in this history of this industry where a module solution lasted against an integrated solution. Let's see. How did Seymour Cray make big, fast computers? That's right, discrete transistors on copper boards with water running through it. And how do you do a supercomputer today? CMOS, with hundreds or thousands of microprocessors, all made in CMOS, cool enough that you don't need water cooling. There's no way that Seymour Cray was a handcrafted, essentially a big module. CMOS wiped it out. CMOS wiped out IBM in the hardware business. CMOS wipes out everything because it can integrate. So as we scale these channels, we get more and more GM. We can do all these other things, and basically we change the industry because once we shipped that 1 billionth and then 2 billionth chips and then went public so all our competitors could see just how penetrated we were into all these markets, they literally within months had switched to SOI. Just like Andy Grove did back in 1983 when he said, I'll never use CMOS. Or you see this throughout history. There's actually a recorded member of the board of directors of the Standard Oil Company, the most powerful company and the richest man ever in the United States. And he had a board member that said, there's no oil west of the Mississippi. I'll drink every drop. 2 months later, Spindlecop came in and doubled world oil production with one oil well and found the great oil fields of the southern United States. So just because somebody who's already in the industry is saying you can't do it, that's actually, you have to hear that if you're going to be a successful entrepreneur. I was fortunate enough to be mentored by a man named Bernie Vonderschmidt. He was the founding CEO of Xilinx, and you guys, the FPGA company. I met him the afternoon Xilinx was going public the next morning. He had bankers coming and going. He had lawyers coming and going. He had his COO coming and going. Everybody wanted a piece of Bernie. He spent 2 hours because he used to run RCA laboratories, and when he saw what we had, he said, Ron, if you really fix silicon on Sapphire, you've got something. But everybody in the world is going to tell you this will never work because it didn't work for them. But don't be fooled. The risk protects you. I get a chill saying that today because that was a driving force in my thinking for Peregrine for the next 20 years. I thought this guy is one of the stalwarts of the industry. He created CMOS at RCA. He sent it to Japan. The whole fabless business model came from Bernie Vonderschmidt. He developed color television under RCA. The man is just one of the great unsung heroes of the industry. And here he is telling me risk protects you. I thought risk was a 4-letter word. I thought what goes with risk? Risk avoidance, risk control, risk management, risk analysis, not risk embracement. Did anybody ever heard that phrase? Bernie told me that. But he said, here's why. Because if you're onto something, your biggest concern should be that there is a big company with more resources who's onto the same thing. And if they really believe in it like you do, they're going to clobber you. You actually have to have them saying this will never work so that they don't throw those resources at it. Gives you the time to put all the barriers to production behind you and in front of them, and then you can compete with the big guys. So if any decision you make does not include a substantial element of risk, you should run away from it because it's probably essentially a poison path for you. So this is some technology stuff. This is a 1/4 micron transistor. This is in comparison. It's an Fmax chart. Fmax is the maximum power you can get out of a transistor, not the maximum frequency at which it will conduct current. So F sub t is basically the length of time it takes for an electron to get across a transistor. That's essentially what F sub t is. It's channel length and it's mobility. This technology won't help that. It's just that simple. But Fmax is how much power you get out versus how much power do you put in. When has that got a unity ratio? And in all those bulk devices and things with a whole bunch of capacitors to ground, guess where most of the power goes? That's right. At 30 gigahertz, it goes right through that capacitor into the substrate and gets dissipated. So you get way less power out than you put in. If you're sitting on Sapphire and you put power into let's say the source, or it's coming out the drain, it sure ain't going through the Sapphire because it can't conduct and there's no capacitor there. So that means all the power has to come out. So the Fmax of this transistor is approximately the same as Fmax of a pHEMT, which also has a semi-insulating substrate. So while the F sub t's are the same as bulk, the Fmaxes are typically 3 to 5 times higher. That changes how you design transistors and how you design circuits. You have to design circuits around Fmax rather than F sub t. If you look at most circuit designers who are used to bipolars, bipolars have wonderful current gain, so they think in terms of F sub t. Of course they do. Fmax is no better on a bipolar than the F sub t, usually less. So that architected thinking differently, it does determine what products you make, etc. But it's an interesting factor. that the F max of our quarter micron transistors were approximately equal to then like 70 nanometer transistors coming out of IBM. So we knew we had a big advantage. Remember, a quarter micron fab, mask sets are $15,000. A 70 nanometer fab, mask sets are $1 million. And you get to spin them 2 or 3 times in RF to get things right. And there aren't that many fabs that'll do it for you. So it's, you know, it's actually nice to be able to use old technology and old facilities, fully depreciated, instead of bleeding edge state of the art that's incredibly expensive and maybe not even stable. So we realized we had linearity, we had F max, and we got to use old fabs. Seemed like we could do something. Here's some data. This is one of those early mixers where we were single IP3s up in the high 30s at the time. That was easily the best single FET quad mixer available. Isolation, Sapphire is magnificent. To this day, Dan, correct me if I'm wrong, I believe we're the only company that can meet the FCC Type 15 spec for a TV that has a cable input and an FM radio or an antenna input. Because you have to have that, a huge amount of isolation, 80 dB, so that the cable signal doesn't go out your antenna and give it to your neighbor. So most TVs, they either have, in fact, almost all of them have our chip in it for that reason. They don't have to get waivers. So that Sapphire isolation is just magnificent. Then we started asking ourselves, what else can we do with this? And basically what we realized is because our transistors were sitting on Sapphire, they're completely independent. You could stack them up and you could put RF on a stack. And it not only will divide amongst those transistors, just like as if you had soldered them together on a PC board, they'll divide perfectly. Why? Because the nearest parasitic is, it's in Chandler, it's in Escondido somewhere compared to where we are. There's virtually no parasitic capacitance to worry about, so the voltage division was perfect. So we started working on this back in the early 2000s. In fact, maybe a little before that. And basically it shows if you have 1, 2, 3, 4, 5, 6, 7, 8 transistors, they all can handle, let's just say 3 volts because I can do the math. 8 times 3 is 24 volts. 1 watt in 50 ohms is, I've forgotten, 18 volts or something like that. So you can handle a watt with a bunch of 3-volt transistors. So with that realization and developing this, we realized we can not only handle power, we can do it incredibly linearly. But when you hit these stacks with high power, when that voltage goes negative, it starts turning on the bottom transistor. So you have to have some negative voltages in there to hold things off at high power. So we had to come up with spur-free charge pumps. Those of you know who Giora Goldberg is, founder of SciTech. He used to work for us. When we said we were going to do this, and we're going to put the charge pump, and we're going to put the level shifters, and we're going to put all the digital logic, and we're going to handle, at that time, GSM levels of power, which is 4 watts, 2 watts into 50 ohms. No cell phone works in 50 ohms. The antennas suck. So you add a VisWire of 8. We just said, screw it, we'll just go to VisWire of infinity, which doubles the voltage, which quadruples the power. So a 2-watt switch we designed for 8 watts. That way, VisWire, schmizwire, we didn't care. Why? Put on more transistors. They're free. Almost. So with this, we could take what at the time was a 35 square millimeter switch module for a GSM phone, and we took it and reduced it to a single chip, and by flip chipping that onto a ceramic substrate, we reduced 35 square millimeters to 7.5, 8.5, something like that. It was a 5x reduction in the area. It reduced the component cost. They didn't have to, because we had the control logic, they didn't have to buy a control chip. They didn't have, we took care of the spurs, the spurs in the charge pump. That's what Giora said you'll never succeed at. You'll never get the spurs out. They'll show up in the radios. Thanks, Giora. The wrist protects you. We found a way, Dan and his team found a way to get rid of all these problems. And today, literally, we have about 1/3 to 1/2 of all of the RF switches in cell phones. And today we have 100% of all the LTE advanced switches in cell phones because we've come out with now our 10th generation of technology that improves all the performance metrics by at least one entire generation. So this was a very clever development. It came from the inner insulating substrate, and it allowed us to deliver linearity and power. I mentioned public safety radio. We actually make a switch for them. No, we don't make a switch for them, but we actually make a 30-watt switch. You can do the math. 30 watts, if you got to have at least 10 transistors. Oops, there's that factor of 4, so we stack. Some of our chips have 15, 18, 20. You just keep stacking, you can handle more power. And this is an example of what it looks like. We actually have gone in, done these simulations, and this voltage division is literally perfect, which means there's no compression, there's no more voltage here than down here. Every transistor is operating in the same place, so it behaves linearly. I mentioned this chart. I want to show you what's behind that, because we said, oh, 1 billion, 2 billion. How'd you get to 1 billion? We weren't born that way. In 1995, we hand-delivered 100 chips to a company called Cytec, which is founded by Georg Goldberg. And that was where it started. I kept telling the company, I was CEO at the time, and I said, the true test of this company is exponential growth. The only number that exponential growth doesn't help is 0. You can double that every year. What do you have? You still have 0. But if you can get to 1 and double it every year, you've got something. Compound interest, basically. So we focused. It took us 5 years to deliver 100 chips. So this is what exponential growth looks like. It's lumpy, but on average it's there. Moore's law is exponential growth. Lots of things are exponential growth. Nature is exponential growth. That's why there's a little bit of that white stuff on your houseplant and you come back tomorrow and it's covered with it. That's exponential growth. So this, to me, is the only true measure of an entrepreneur is exponential growth. We talked about that, but this is the measure. Now, eventually it does saturate. I think we've gone, this was 100 million, we crossed a billion. It took us 2 more years, so I could put those dots in out here. It would be around 2013. So it might be interesting to put that. We may still be on the same curve. Almost doubled every year for 17 years. And it's a testament to the employees. It's a testament to their spirit. It's a testament to their entrepreneurial spirit. And on that score, I want everybody to realize you don't have to be a founder to be an entrepreneur. The employee who was number 4 was an entrepreneur. The employee who was number 10 and had a nice big job offer with matching 401k from Qualcomm, turned that down to come here, that person is an entrepreneur, because compared to the giants, we're still an entrepreneurial startup. We may be public, we still have that spirit, and we know we can keep driving a curve that looks something like this. In 1988, I came home one day, decided I wanted to start the company. I went to my wife and I basically told her this. I said, look, I have a tenured government job. I have a guaranteed pension. We have $8,000 in savings. We have 2 kids that just entered college. We just bought a house we can't afford. I have a lab full of incredibly expensive equipment, and my boss works 3 miles from me. He doesn't even know if I come to work. And I want to abandon all of that and go start a company. I fully expected her to say, would you go over all those highlights again? Instead, she said, if that's what you want to do, we'll find a way to make it work. She's my co-founder. Subsequently, I asked the other folks who actually did the work, but if my wife had said no, or 2 years, let one of the kids out of college, this wouldn't have happened. So that spirit, in many ways, I didn't know it at the time, but I subsequently learned from Bernie von der Schmidt, the risk protects you. That's the goal. That's the angel that actually protects everybody. You can, look at Microsoft, look at Intel. They went through near-death experience again and again and again. They were making great money on memory, and Japan Inc. decided they were going to just bomb the memory market worldwide. Intel went through an existential change, and that was 1980 basically. So that risk protects you is absolutely a spirit to keep up with. I put this up here because this was my boss and my mentor, probably my strongest mentor in my life. Everybody has a mentor. If you don't know who yours is, think about it. You have one. And those people can actually guide you. They can help you. I had another mentor in Bernie von der Schmidt. But Isaac was an incredibly demanding boss, but he believed in what we were doing, and he wanted to see this technology not succeed just for the military, but he believed the military would get nothing out of it if it didn't find a commercial home, because the military doesn't make things anymore. If commercial industry can't do it, they really can't do it themselves because of the costs of the infrastructure to manufacture. We picked RF. Early on, we went to the Consumer Electronics Show in Las Vegas, and I asked all the employees that went to that, I want you to walk around this show. This was 1991. I want you to count how many portable telephones are in use, not being carried around in luggers, but actually in use, and how many portable computers in use. 2 days later, we added it up. It was 30 to 1. So I thought, portable computers are amazing. Portable telephones are going to take over the world. And this is when it was $1 a minute. And these things were being outused over computers at the rate of 30 to 1. So we picked the wireless market. We knew our advantage, that Sapphire substrate. We knew CMOS would eventually win. This market would get so big eventually it would need CMOS and CMOS integration. Subsequently, we got a bone from nature in this linearity thing, but the fact is that's what we decided. That's my co-founder, Mark Bergner. That's Georg Goldberg, for those of you who know him, and Tony Morrow, who is the president. And this is Jim Cable when he joined us in 1996. I hired him as chief engineer, and he subsequently became CEO in 1992. I raised $18 million from friends and family, and now ex-friends and ex-family, and dead friends and dead family, and people standing at a bus stop. If you had a wallet, I was asking you for money. Jim Cable raised over $200 million. This guy, the company wouldn't exist without Jim. He is way more just the CEO. He is absolutely in every fiber of this company. We've been to every planet except for Uranus, and the only reason we haven't been to Uranus is because the US hasn't spent a space probe there, I believe, ever. When our chips were launched to Pluto, it was still a planet. So I don't know if we count that one or not, because it only takes like 18 years to get there, and by the time, I don't know, what do? Retarget? Hey, don't go there, go over here. That thing's not even a planet anymore. So maybe after they take some pictures, they'll decide it really is a planet. This is when we got into these integrated switches that subsequently we shipped 1 million pieces in 2000. That was on that chart. From 100 to 1 million is that exponential growth. Anybody who comes in and says, oh yeah, but 1 million's easy. We do it every 6 hours now. You weren't here. We didn't have factories like this. We didn't have 50 testers. We didn't have quality department. We had about 50, 20 maybe entrepreneurial people who would do everything from sweep the floor to test the chips. Every bit of that exponential growth is hard because you're doing it with what you had last year. So every step is hard, but every step is a measure of your success. We got into handsets in around 2004. I believe that's the first chip we shipped into the GSM market. You can see the bumps on it. We introduced flip chip. We introduced single chip. We introduced integration. We collapsed the size. And the gallium arsenide guys had no choice but to go in and badmouth us. Okay, the wrist protects you. We invented HARP. Our linearity, as I showed you, our transistors should be perfectly linear, and they weren't. They had this trace amount of nonlinearity, and we struggled. We literally couldn't figure out where it was coming from. So we actually launched an activity. We could see that with CDMA and WCDMA and more demands for linearity, we had to we had to find out why our transistors weren't perfectly linear. So we launched an activity, and we discovered the cause of the mystery nonlinearity. We eliminated it. We patented it. We've been using it ever since. Our competitors are stealing it from us, and they're using it to great success. But the point is, here we are, 2005, over 15 years since starting the company, and this was the second greatest invention other than the basic material. This was the second greatest invention in the history of this company. So 15 years later, we're still innovating. We're still finding a way to solve the market's problems. We didn't have any money. Our VCs were tired. We were in one of those out of money, out of altitude, and out of ideas for a pilot, basically. But we still kept investing in R&D because we still believed we had a really great story to tell here. We headed to Pluto. We didn't call it a planet here. I was going to tell you a story. The first Mars lander landed on Mars. I happened to be on Hawaii with my wife on vacation. And I was ready, she wasn't. Anybody heard that story before? So I turned the TV on, and it turns out the Mars lander was just entering the Martian atmosphere. And on that one, there was a 17-minute blackout period. So we knew the radios were working. Our chips run the radios, they're the phase lock loops. We knew our chips were working fine, but we really wanted to know our chips were going to work on the surface of the planet. So we're waiting for the 17-minute blackout period. There's a picture of the JPL control room. They're all looking like this, and all of a sudden 17 minutes comes, nothing. It's like Apollo 13. Where are they? 17 and a half minutes. It turns out it's about 17 minutes. They didn't tell us that. all of a sudden, every engineer at JPL just jumped up in the air and screamed with delight because there was a radio signal, which means it landed safely and the radios were working, which meant our chips were working. So I look over at my wife and there's tears running down her eyes. This is 15 years after we start the company. Go down to dinner. We knew the waiter quite well. I apologized. I said, you know, I'm sorry, David, but this is what we just did. That's why we're a half hour late. And so I said, you know, when you're a kid, what are the chances you're actually going to be involved in building something that goes to Mars? And he looks at me without hesitating. He says, what are the chances you even know somebody who did that? And I just thought that was a perfect encapsulation of the rewards for going and doing something different, is that you can be that somebody that somebody else just is happy to know about because of an accomplishment, not that you did, but that your employees did and that your companies did and that your entrepreneurial spirit did. And every one of you has that in you. Every one of you has an idea. You may or may not follow it, but it's there, and at least listen to it. We actually were on the spacecraft that went to this asteroid. I've forgotten the name of it. It's a funny asteroid name. The spacecraft was launched by the Japanese Space Agency, and the spacecraft's name was Hayabusa. Turns out Hayabusa translates in Japanese into Peregrine Falcon. So we always thought, oh, that's pretty cool. It landed on an asteroid, which is almost impossible because there's no gravity. It's like literally 10 to the minus 6 Gs. So, and they wanted to get dust without contaminating, so they had to figure out how to land and essentially land on a planetoid with no gravity without spraying it with the exhaust from the fuel. And it's really amazing. They land on it, they scoop up a little dust, and they brought it back. I think it just landed, brought the dust back from this asteroid. It's very cool. So this is not what runs the company. It isn't what makes us all the money. It's a very good business for us, but it's those fun things, and you have to keep embracing that. And finally, last year in August, we went public. That's Jim Cable. There's Mark Berger and myself. So as an entrepreneur, I have to admit, they say going public is the beginning. It may be the end of the beginning, but it's not the end of the road. But it is certainly the last box you check, because you can say the market has accepted your creation.